SwayamPrabha. Digital India. Educated India.
Okay, so in the previous class, I gave a brief background on the need to perform experiments and the quantities that we measure in dispersed multiphase flows in experiments and the objectives of this module of the course. So, now we will look at the classification of measurement techniques in multiphase flows. So, the measurement techniques can be broadly divided into two categories. One is based on sampling methods and the other techniques are based on online methods. So, what is sampling method? Sampling method basically refers to the case where the flow is sampled. So, you take out some part of the flow and then you separate them and you analyze it separately. So, this is called sampling method, which itself can be based on imaging or mechanical methods, analytic methods or some specialized techniques we can use. We will look at this soon again in somewhat more detail. Now, on the other hand, we have online methods which differ from sampling methods in the sense that here we do in situ measurements, which means that the measurements are taken in the flow when the flow is happening. Okay. So, this can be of two types. One is integral method, one is local measurement techniques. Integral method means here we get the information about, let us say, particles which are integrated over some distance. For example, let us say you have a flow carrying particles, your technique gives you the particle size which is integrated across the flow. This means that you do not get local measurements, but you may get particle size distribution, but that would correspond to the integral value. Okay. On the other hand, we have local measurement techniques which can locally measure, let us say, the particle size distribution. This itself can be intrusive, non-intrusive. The intrusive techniques again can be point based or field based. Point based means your measurement probe volume is very small such that it can be treated as a point. Field based means you get information across a larger area or a larger volume. Yeah. So, online methods are done inside the system and usually in real time. Now, sampling methods, as I said, in this case we extract small fluid particles, particle sample from the flow, we send it to the lab for measurements and we can measure size, composition, concentration, etc. Examples include filtration. So, in your multiphase system, somehow you filter the particles and then you use a microscope to observe the particles, and that is how you measure the size. Or let us say you use advanced technique like, let us say, scanning electron microscope to measure the particle size, particle morphology, etc. Other simple approach, for example, includes sieving. I think once I gave this example. So, here you have, let us say, a mesh where you put the particles. Let us say you want to measure particles in a spray dryer, particle size in a spray dryer. So, you can have sieves which are essentially meshes of certain mesh size. So, you put the particles on the sieve and you collect the particles below. So, you can collect particles which are smaller than the size of the mesh and you measure its weight, and you keep on doing this for smaller and smaller mesh sizes. So, what you measure essentially is cumulative mass distribution. So, you will get cumulative mass distribution, and if that agrees well with some theoretical distribution, let us say Rosen-Ramlet distribution, then you can get the probability distribution from the measured cumulative distribution. Okay. And we have gravimetric analysis. So, in this case, let us say you measure the, you want to measure moisture content in coal particles, then you keep the particles in a weighing balance and you heat it up. You heat up, you maintain the temperature such that only the moisture evaporates. Then you measure the weight again, and that gives you the mass of the moisture. So, similarly, you can heat up at different temperatures to allow release of, let us say, volatile components, and finally you can burn it and finally see what is the ash content in the coal. So, that is how the composition can be measured. There are other specialized methods, for example, electrostatic collection, chemical absorption, thermal extraction. So, all these methods are the sampling methods. So, in which you take out the sample and perform the measurements in the lab separately. The advantages are it can provide very detailed chemical physical composition, and we can obtain high accuracy for size and mass distribution, mainly because this is not real time measurement. But on the other hand, we have limitations that here we disturb the flow. When you take out the sample, you will disturb the flow, and importantly there is no temporal resolution. So, you cannot get any information about how the particle size, let us say, varies with size. It may change from start of the experiments or start of the measurement to the end. So, the particle size may change. Now, let us say again, for example, you measure particle size distribution in a spray dryer, and you see that you get larger number of particles, larger number of large size particles than you expect, but you have no means to find out if you obtain those particles in the initial period, during the initial stage. So, if you know that, then maybe you can modify your flow configuration such that you can avoid that problem, but in this case you will not have the flexibility to know this. And we have also limited spatial resolution. So, if you want to measure the local particle size, so if you have this spray dryer, and it may be possible that at different parts this particle size distribution is different, but it is difficult to get using this approach. Okay, so this is about sampling methods. We will focus mostly on the online or in situ methods of measurement. Now, this requires some basic understanding on light particle interaction. So, till now we have discussed particle turbulent interaction, but light particle interaction is also a complex and a fascinating phenomena that has attracted significant attention over a century. So, since a long time people wanted to understand light particle interaction. So, why it is complex? Let us see that. So, imagine you have a beam of light, okay, interacting with one particle. Now, we can have different phenomena. What are those? Absorption. Part of the light might be absorbed by the particle and converted into other forms of energy, for example, heat or fluorescence. So, that part of light energy is absorbed. So, in fact, this is the reason why we define refractive index as consisting of two parts. One is the real part, which we know what is refractive index, that is the ratio of the speed of light in vacuum to speed of light in a medium, that is what is refractive index. However, the imaginary component basically governs the absorption phenomena. So, this imaginary component corresponds to this absorption. We can have also scattering of light. What is scattering? Light is redirected in many different directions as it interacts with the particle. We can have reflection or refraction, which you are aware of. We can also have diffraction. Diffraction means when light bends around the edges of the particle, producing an interference fringe pattern. This is similar to Young's double slit experiment that you would have come across in your earlier studies. Now, why it is complex? Because all these phenomena depend on particle size, shape, refractive properties, for example, refractive index, which itself can be a function of temperature and density, as well as the wavelength of the incident light and also the polarization of the incident light. Polarization of the light means it refers to the direction of the electric field. So, essentially light is an electromagnetic wave. So, the direction of the electric field basically refers to polarization. For instance, if the direction is in the plane of the wave, then we have parallel polarization. If the direction is perpendicular to the plane, then we have perpendicular polarization. Okay. So, all these factors influence the outcome of the light particle interaction. Okay. So, this is an example of how light behaves as it interacts with a particle. Okay. So, here what you see here is basically the scattering intensity in the near field of a 20 micron droplet, which is exposed to a Gaussian laser beam. Okay. So, what do we see here? So, in this case, the refractive index is 1.3. So, this is water, you can say. So, for water you have refractive index 1.3, and you have, this is the wavelength of the light, and here parallel polarization has been used. So, now what is interesting is, as this light incidents on the particle, one part of the light is reflected, okay, but the other part undergoes refraction. So, this part comes here, and after this you have one internal reflection and one refraction, which is known as first order refraction. This is the first time you get the refraction. This is called first order refraction, and the reflection is also called zeroth order refraction. Okay. So, this is usually denoted by P is equal to 0, P is equal to 1, but this phenomenon does not stop here. The light, this internally reflected light again gets reflected inside and one part comes out. This is called second order refraction, and it does not stop. It goes on here, okay, forever. Okay. That is how we have different, and similarly we have third order refraction. Now, here we may have diffraction or bending of light in this zone. So, what I explained, you can see in this simplified diagram the same thing. So, this part is reflected. Now, what detects the angle of refraction? That is according to Snell's law, what you have already studied, that is m1 sin theta, where theta is the angle of incident with respect to normal, is equal to m2 sin theta 2. Here 2 corresponds to this medium. Okay. So, if the light is travelling from rarer to denser medium, then it will bend towards the normal. Okay. And so, accordingly you can find out what is this angle. Okay. And then we have this as P is equal to 1, this is P is equal to 2, this is P is equal to 3, and so on. So, now the question is, why are we discussing all this? This is because different optical techniques exploit various outcomes of this light particle interaction to measure particle properties such as size, shape and refractive index. So, this is the reason why we need to understand the light particle interaction. We will see this later, how when we discuss individual techniques, how they are based on these different phenomena that we see around the light, I mean the interaction phenomena. Now, light scattering theory. So, what is light scattering theory is that it describes how electromagnetic radiation, or in this case light, interacts with particle and is redirected from its original path. So, this is mainly described by Maxwell's equation with boundary conditions applied at the particle surface. So, you imagine like we have Navier-Stokes equation. If you want to solve flow around the particle, around let us say you have a spherical particle and you want to solve the flow. So, what you need? First you need the governing equations, which are Navier-Stokes equation. Then you need to impose the boundary conditions and then you solve. Exactly in this case, Maxwell's equations can be solved by imposing the boundary conditions at the particle surface. And if we solve these equations, it provides the field, the light intensity field around a particle. So, if you consider, let us say you imagine you have a particle here and you illuminate that say with a laser light. Let us say room is dark. What do you see? You see one bright spot, that is all. But interestingly, the light intensity varies in a very interesting way around the particle, and it need not be isotropic, it need not be same all around. Okay. And this was actually first done by a scientist known as Me in long time ago, more than 100 years ago, and sometime later by Debye a year later. So, both these scientists could solve Maxwell's wave equations for a spherical particle. And what did they get is, this is the simplified form. So, here E naught refers to the intensity of the light, incident light on the particle, and E refers to finally what you get, the intensity around the particle. This is of our interest. So, you see that the intensity of light depends on several parameters, including this important parameter called shape parameter, this size parameter, this is called size parameter, which is basically the ratio of particle size to the wavelength of the incident light. Okay. And also it depends on the refractive index, also it depends on the angle. So, if this is your particle, then the light intensity would depend on the angle at which you want to collect it. Okay. So, the light intensity here and here basically are not same. Okay. Now, in the context of light particle interaction, this zone is called forward scattering zone. Here you have forward scattering and this is called backward scattering, when you have this as your incident light. Okay. Now, we have the solution for this. So, basically we know this function, okay, which is known as the amplitude function, which characterizes the amplitude and phase of the light. Okay. You have a complex function, I am not showing that here, but you can only keep in mind that we know this function. Now, what do we want to do? Now, if we have this theoretical description of light scattering by particles, then we have an inverse problem. What is the inverse problem? In an experiment, what you measure is basically the intensity at any direction. So, now you know the intensity. The question is, can you calculate the particle size? You can calculate if you know the relationship between the light which is scattered and the particle size through the theory. So, this is the basic idea of the measurement technique. I hope this is clear. So, we want to measure the scattered light in all cases, and from that how can we measure the particle size as far as measurement of particle size is concerned. Okay. Okay, so this is to demonstrate how the light intensity behaves around a particle. So, in this case, in this example, one particle of a given size is taken, and here we specify the particle in refractive index, we specify the polarization of the light, we specify the wavelength of the light. Okay. And by solving Maxwell's equation, or you can say this is Me or Debye solutions. So, here what you see, this one, this gray one basically refers to how intensity varies with respect to the scattering angle. So, here you see this is 0, this means this is forward scattering zone. So, the light intensity reduces and then it increases, and you see some oscillations also. Okay. So, this is how actually light intensity is around a particle. But the advantage of this solution is that we can segregate this for different orders of refraction and individually calculate the intensity due to each order of refraction. For example, we can fix reflection. Okay, in this case they have taken p is equal to 1, this is sometimes called 0. So, only reflection, how the reflection intensity around the particle is. Now, this green one gives you that. So, you see that at some angle the reflection becomes 0, or the reflected light intensity becomes 0. This is known as Brewster angle. Okay. So, similarly, you can have first order, second order, third order light intensity individually. Also, we can combine. I mean, if you want to see the combination of p is equal to 0 and p is equal to 1, that also you can do. There is a freely available software called MePlot. You can download this, and this is a very user friendly, they have a very user friendly interface. So, if you already there are some default values, okay. For example, particle size, wavelength are given, you can change that also. So, that there you can do all this and you can see the variation of light intensity, okay, which is very useful. Okay. So, now these are example of how the light intensity is around, let us say 1 micron oil particle. Okay. So, and when you change that to 10 micron, now you see how the particle intensity distribution has changed. So, this is shown in a polar plot. So, the final point is that the intensity distribution around a particle is need not be same. Okay. If the particle size is very small relative to the wavelength of the light, then we approach isotropy. Isotropy means the intensity distribution would be same all around. Okay. Otherwise, it is not. Now, we can also integrate all this. If we integrate this, we can get one value, integrated value of intensity. Okay. So, that integrated intensity is shown here with respect to Me parameter. Me parameter means it is this one. Basically, the ratio of the perimeter to wavelength, or you can say size to wavelength. Now, what you see here is that when this parameter is much below 1, then we have relationship like this, and also see this is at 30 degree, this is at 90 degree. So, if you change the scattering angle or you change the angle at which you detect the intensity, the relationship can vary. But here you see that it is quite sensitive to the size parameter. Okay. So, this is called Rayleigh scattering. You all have experienced Rayleigh scattering, how sky looks blue because of Rayleigh scattering. Okay. And in this case, the particle size is much smaller than the wavelength, and this is what happens in upper atmosphere, where we have air molecules or aerosols whose size is smaller than the wavelength of the light. And what is interesting is that it scatters mostly the blue light. So, in sun ray we have all 7 colors, but it scatters the blue light more compared to any other wavelength. So, that is the reason why we see that the color of the sky is blue. Now, when the Mi parameter is about 1, so this parameter is about 1, which means that the particle size and the wavelength are of similar order, then we get the exact electromagnetic solution what we discussed just now. So, in that case, the scattering intensity is now not same, and it varies with the scattering angle. And we have seen that here we have complex angular dependence, and this forward scattering is strong. So, in both of those examples what I have shown, you might have noticed that the forward scattering intensity is quite strong. And what are the examples? Fogs, clouds. When you see a cloud, basically we see these Mi scattering from the particles, and the particle size there is typically of the order of 10 micron or so. So, that is why the particle size now has gone up. That is the reason why you see Mi scattering. Now, if the size parameter is quite large or larger than 1, then we have geometric optics zone. Geometric optics means here we can treat light as rays. What is meant by this? What I had just shown. So, in this case, it is possible that you can go on drawing the light rays, okay. And then, so you say using Snell's law, I calculate, I know at each point what is the angle and how it will deflect, and I can do that at all interfaces, and I can theoretically calculate the behavior of light, okay. And this is called geometric optics. Now, the advantage here is that we do not have to do the rigorous Mi solutions for Maxwell's equation. It is not required. Just by ray diagram you can calculate and show the path of the light and do your analysis. So, that is the advantage, but this you can do only when the size parameter is large. And this also explains rainbow. For example, whenever you see a rainbow, what you see is the light which is backscattered. So, in case of rainbow, the what we see is backscattering. So, this is the forward scattering, this is the backward scatter light. So, you see the rainbow in front of you. So, and this angle is, I think, about 138 degree, this backscattering angle, okay. And this can be explained using the geometric optics, okay. Now, we move on to, with this background, we move on to discuss our experimental techniques, which are the optical techniques. In general, these are non-intrusive techniques, okay, where some form of light is used to illuminate the particles. The first one in this category is laser Doppler velocimetry technique, which is a local measurement technique, in situ measurement technique, okay. It is not integral. This is real time measurement and local measurement. Now, LDV or laser Doppler velocimetry is a non-intrusive optical technique which is used for measuring velocity of fluids and gases. When this was developed, the idea was to measure velocity of fluids and gases. You can now ask, okay, how about multiphase flows? We will see that later. Okay. Now, the basic principle is that it uses Doppler shift of the scattered light from moving tracer particles to measure velocity. This is commonly used in fluid mechanics, combustion, sprays and turbulence studies. The advantages are it has high spatial resolution, high temporal resolution, and there is no physical probes in the flow. So, when laser Doppler was developed, okay, before that people used mainly pitot tube, okay, where you can reliably measure fluid velocity, but only the mean velocity. But when turbulence theory was developed, people realized that it is not enough. Why it is not enough? Because the temporal resolution of pitot tube is very poor, or the response time of the pitot tube is poor. What does it mean? This means that if you, let us say you have a turbulent flow and you put the pitot tube, what would you expect to see? Do you expect, I assume you all of you know how a pitot tube works. Okay. You basically measure the height, the difference in height in your manometer, if you are using a manometer. Okay. Now, if you have a turbulent flow, what do you expect? The height, should it fluctuate with time? If yes, then can you measure the fluid velocity fluctuation? Now, the answer is mostly no. It may fluctuate, but that won't give you turbulence. Why? Because the response time of this device, response time means if the velocity changes, then how fast the device responds to it, that response time is quite longer than the turbulent time scale, typically the turbulent time scale of the flow. So, naturally you filter out the small fluctuations. If the turbulence intensity is really high, you may see some fluctuations based corresponding to the large ED turbulent time scales, but still you won't get the reliable measurement of turbulence. That is why hot wire anemometer came into picture. Hot wire anemometer has excellent time resolution. So, you could measure turbulence very accurately. Okay. But the problem is that it is an intrusive technique. So, you have to disturb the flow. Okay. So, after that, when laser Doppler velocimetry came into the field, it became very popular because now it is not intrusive. Okay. Now, this is the basic idea that what is Doppler effect, how Doppler effect is used in laser Doppler velocimetry. We all know that Doppler effect basically refers to change in apparent frequency of a wave in relation to an observer. Okay. The popular example is you are standing in railway station and a train approaches which is blowing a horn at a constant frequency, but you hear that the frequency increases as the train approaches to you. So, basically it refers to the apparent frequency. Okay. Similarly, if the train leaves, as it moves away from you, the frequency reduces, okay, or the wavelength of the wave changes accordingly. Okay. Now, imagine you have a emitter. This is a source which emits light, and here you have a particle which moves at certain velocity, let us say v. Now, the particle would see a different apparent frequency of the light, because there is a relative velocity between the emitter and the particle. So, the Doppler effect is not only restricted to sound waves, it is also applicable to electromagnetic waves. So, as this moves, now this sees a different frequency which is known as first Doppler shift. Now, when the light waves interact with the particle, the light is scattered and we have a receiver which receives the scattered light. Now, because the particle is also moving, also has a relative velocity with respect to the receiver, you have now second Doppler shift. So, there are two Doppler shifts coming into picture here. So, it is possible that we can derive a relation like this, where finally this is the Fr is the frequency of the light received by the receiver, okay, and it is related to the frequency of the laser source, okay, and through this relation. Now, before we move away, why did I mention laser? What is the problem if we would use a white light? Let us say one is energy, but if you see the scattering intensity according to the May theory, it depends also on the wavelength of the light. So, if you have multiple wavelength, then obviously you complicate the scenario. So, that is the reason why we choose a monochromatic light source, which means a light source with a single wavelength. Okay. Now, coming back here, so you have now relation between the frequency of the light received by the receiver and the frequency of the laser source, which is known through this relation. So, here c is the speed of light, v is what you want to measure, the particle velocity, and these are unit vectors. So, these are also known. Okay. So, using this relation, if now we measure this is known, this is known. So, we can calculate what is particle velocity theoretically. Okay. What we need to measure is only this. But the problem with this approach is that this frequency that we see here, the frequency received by the receiver is really small. It is a very, very small undetectable frequency. Okay. Now, to avoid that problem, a dual beam approach is used, which means that you have now two laser beams which interfere with each other, okay, and they produce. So, here you have plane wave fronts, and at the beam waist they produce this probe volume, which basically consists of a pattern of bright and dark stripes or planes. Okay. Now, there is a model called fringe model to explain how do we measure velocity. Okay. This is a very simplified, I am saying model, because this may not be the reality. It represents the reality. Okay. It is not the reality. So, this is basically a model. It simplifies the understanding of the principle of LDV. How? Let us see this. So, here as I have shown here, you have a pattern of bright and dark fringe patterns, okay, these bright and dark stripes. So, if I pass through this, I will see that the intensity oscillates like this. Now, imagine this particle is entering. Okay. So, now you are collecting the scattered light from the particle. Here also you can expect this to be oscillating in nature, oscillatory in nature. Okay. Now, we know the distance between two peaks here. It depends on the angle between the two laser beams and the wavelength of the light. It can be shown easily that this distance between the two peaks is given by this. So, now if I know the time that the particle takes to move from here to here, then this gives me the velocity. Okay. Now, what is this? This is nothing but inverse of the frequency. So, that is why we have this relationship. Okay. So, now from this relationship what do we get? We see that if we can measure this frequency, this angle is known, the wavelength of the light is known, we can calculate what is velocity. So, this is the principle, and that is why this fringe model is used. Otherwise, this interaction is quite complex to explain. Okay. So, now considering that the laser beam intensity is not actually planar as shown here. The laser beam, the practical lasers, if you see a beam of laser, it is actually Gaussian in nature. That is, so if this is your laser beam, the intensity, the laser intensity would look like this. So, you have larger intensity at the center. So, that is the reason why the practical Doppler signal, this is called a Doppler signal, practical Doppler signals look like this. So, here you have basically a pedestal effect. So, because the intensity is like this, you see this like this. Okay. So, now we can take Fourier transform of this signal to calculate what is frequency. That is what we need to measure. Once you measure the frequency, essentially you know the time between these two peaks, and that is how you get velocity. Okay. So, this is the, I'll just finish. So, this is basically the flow chart of this or schematic of the LDV technique. So, here we use a continuous wave laser and there is a transmitting optics. So, what it does is that it splits this beam into two parts, and also it introduces a frequency shift, because interference is possible only when there is a frequency, there is a difference in phase or frequency between the two phases. Also, it has another important role, as I will tell you later. And this is how you create the probe volume. The probe volume means what you create at the beam waist, okay, this interference pattern. And then the particles flow through this. There is a receiving optics, which is basically a photo detector or a photo multiplier. This means that this is not an imaging based device. You do not image the particle, you only detect the photons. So, the light which are scattered, it captures the photons and it basically transforms that to a voltage signal. Okay. That is what the role of receiving optics. And once you get the signal, then you need a signal conditioner also, and you need to analyze the signal, or you need to do signal processing, because you may have noise. The signal may not always look as good as this. You may have a background noise, let us say because of the electronics that you are using. So, some signal conditioning is required. And finally, you store the data in your PC. So, basically if you process this signal, you get the frequency. So, let us say if you have a very clean signal, you get a Fourier spectrum like this. Otherwise, if the signal is noisy, then you may see multiple peaks. Okay. And if the signal to noise ratio is high, you may have to reject that information from that particle. Okay. Okay. So, these are some examples of how the Doppler burst looks like as the particle velocity changes. And this is also another schematic of this dual beam laser Doppler velocimetry, or it is also called laser Doppler anemometer. Okay, so here you can see how this beam is split into two parts, and there is this cell which is known as Bragg cell, okay, which is used to introduce the frequency shift, and then here you have the probe volume. These are the photo detector, and then this is connected to your signal processing unit.